thank you everyone for coming. So our speaker today is Qiwei Yao from LSE, where he's a statistics professor there, and it's his last day here until March.
Thank you. The talk is about probably one of the oldest problems in statistics, but we sort of have a new twist now. Testing for white noise. Some people view this is one of the most important tests in statistics because lots of like linear regression modeling, when you do the diagnostic checking, it can be sort of transformed into a white noise test. So my sort of understanding of this problem is on one hand, it's a very old problem. On the other hand, it's not sort of well solved problem, even in the univariate case. I guess the difficulty here is when we do the model diagnostic checking, we typically don't have an alternative. We just test none is a white noise. Alternative, it could be any kind of departure from white noise. So this makes the task more challenging. If we have a specific alternative, we know we can use likelihood ratio, which probably is the best you can have. But since we don't specify an alternative, so you try to detect the departure for all possible kind of directions. And this makes those omnibus tests typically less powerful than the likelihood ratio based tests. Why we look into this older problem? This is because sort of, and for those you know me, I have been doing this high-dimensional time series modeling, especially factor modeling. When you fit a factor model, you need to decide how many factors. In a sense, original time series subtract the contribution of factors, remaining should be a white noise. So this is kind of, in the high-dimensional time series, is a high-dimensional white noise. We knew from day one the existing tests will have problems in coping with the high dimension. But we have been sort of waving our hands all the way around so far. And what we did is, okay, we look at high dimensional residue. We try to project residue into the direction such that the serial correlation are strongest. Then we just look at each of those univariate directions. So whether this univariate projection is white noise or not. And to do this, of course, there is a kind of extreme value idea kicking on because you look into the direction which is serially most correlated. So this is looking for kind of maximum of statistics. So apply the traditional univariate test is not appropriate. But for a long time, I didn't know how to tackle this problem. So then I sort of keep talking to people when I have them sort of around me. We are working on those kind of problem. And eventually, and you can see two sets of coders come up with different solutions. So I will give you a brief introduction of those two approaches. So this is the kind of background why we look into this problem. Here's the outline. First, I give you some intuitive explanation. What's the problem when we try to test the white noise in a high-dimensional setting? Then those are two methods. One is based on the maximum auto cross correlations, and the statistic itself is very intuitive. It's still very much in this category of the omnibus tests. We don't have a specific alternative. We just try to use something intuitively reasonable as our test statistics. The problem is try to work out the p-value, and the way we solve the problem is use the bootstrap by the normal approximation, which intuitively is very simple. There's a computational issue in the high-dimensional setting to implement this procedure it's a computational intensive problem. This n is the sample size, is the length of time series in this context. P is the dimension of time series, how many components of time series we look at. So we managed to reduce the problem from this hard to the n2 cubic, which is still a sort of very tough problem, but that's kind of difficulty we have to live with. Then we spell out some asymptotic properties which justify this bootstrap procedure. Then I show you some numerical properties. So this is one approach using the maximum auto or cross correlations. The second approach is using the random matrix theory. Actually, as you can see, I had some idea because we have been doing this. As I said, try to project a high dimensional into low dimensional, looking for maximum, or looking for a direction which has a maximum serial correlation. This can be neatly recasted into some kind of eigenvalue problem. You work with a function of autocovariance matrix. This is a matrix function which is positive definite. Then you look at the eigenvalue, and the maximum eigenvalue corresponding to the direction, which is also serial correlated. So therefore, what you really need to test is whether this maximum eigenvalue, based on the data you have, corresponding to a true value, which is 0. If it's white noise, all those eigenvalues should be 0. So the testing problem can be very neatly recasted as a test a single maximum eigenvalue of a positive definite matrix. But unfortunately, we cannot do that. So those are sort of kind of compromise. And the advantage, as you can see, the two sets of tests are designed for different scenarios. This is typically sort of for a case when the correlation are sparse. Yeah, actually, the sparse cause a problem for the classical problem, and this, as it turns out, is sort of designed for the case, the correlation across all over the places. Okay, that's kind of for plan. First, let's see what's the problem of the classical test for the white noise. Now we assume epsilon t. This is our observation. Yeah, and the reason we use epsilon is because, as I said, the most frequently application for white noise test is to do the model diagnostic checking after fitting the regression model, for example. So epsilon t is typically the noise term, or estimated is a residual. But for the simplicity of presentation, we start with, say, we assume epsilon t. Then later on, we come back, say, what we have derived can be applied to the case when epsilon t actually is a residual from the fitting regression model. So epsilon t is observed time series. We assume it's weakly stationary. That means mean value in this case is assumed to be 0, and the variance is a constant matrix. And covariance, autocovariance, only depends on the lag between the two random variable, time lag. So this sigma k is autocovariance. Then to work out the autocorrelation matrix, you need to divide it by the variance of the two components. In matrix form, this is the autocorrelation matrix of this vector processes. The so-called white noise test is really just to test the linear independence. So what we try to test is this autocovariance matrix at the non-zero lag is 0 for all lags. Okay, the classical test, this is a box portmanteau test and its variations. I didn't list all of them. I guess the fact that there are so many variations itself manifests the problem of this test. The box Pierce test proposed in the 70s in this original form is very intuitive because you want to test, say, the no linear correlations. So you just add all those linear correlations at a non-zero lag, this matrix times transpose, then take trace. Basically, you square every element of the matrix, then add them up. Because if it's independent, then all those elements should be zero. So intuitively, this is very clear why we use this as a statistics. And you add the lag from 1 to, say, capital K. Yeah, capital K is like a tuning parameter in the test. So if you write it in the component-wise, it's in this form. Then this is original box-pierce test in the multivariate case. Then Hosking proposed a variation. The variation is that you insert an n here, then you divide it by n minus k for each time lag. Suppose that k, capital K is a constant, then asymptotically this is equivalent to this. But actually, when they prove the asymptotic chi-square approximation, they let this k goes to infinity slower than n. Only then you can get a chi-square approximation. So this is a kind of empirical modification such that the chi-square approximation we mentioned in minutes will be better for this statistic than this one. Then Lee, McLeod, actually this is W.K. Lee's PhD thesis. Yeah, they proposed another modification. McLeod is his supervisor. Instead of taking n square here, they add a constant term. Yeah. So those two are variation here. But nevertheless, as we can see, if you let capital K goes to infinity at a slower rate than n, those three statistics are asymptotically equivalent. And they all have a chi-square approximation if epsilon t is IID. This is really sort of embarrassing because what we try to test is the linear independence. But to prove that this test under H0 has a chi-square approximation, we assume it's IID. Yeah? Every time when I teach this test to students, I feel awkward. Yeah? We are not genuinely test IID because if you really want to test IID, you should look beyond the linear dependence. Yeah? But if you want to test the linear dependence, you need this IID condition in order this theory to hold. Of course, you need the fourth finite moment as well. So that's the result, classical result of Portman-Teal test. And one of my colleagues told me that he had found a real data set such that you use this test, that's a univariate case, even univariate case, by choosing different k according to this approximation. You can get any kind of p-value as you like for real data set, which is really worrying. What's happened in practice now is, especially in the econometrics literature, people apply this test with different capital K. List all p-values. If all p-value point to the right, point to the same direction, you are happy. Yeah? If not, case is inconclusive. Okay. What's the problem? I mentioned one. This is kind of awkward situation, IID versus white noise. Yeah? Second, when p is large, the dimension is large in relation to n, this chi-square approximation is poor. It's so poor such that make all those tests powerless. You intuitively think there's nothing wrong with the test statistics, yeah, or nothing fundamentally wrong with test statistics. But when p is large, those tests really have no power. We run a simulation to show you the problem. Say we compare the two distributions. One is a true distribution of each of those test statistics. You can do simulation, yeah, use empirical distribution from simulation to approximate the true distribution. Then we compare this distribution with its chi-square approximation. The degree freedom p squared, p is the dimension of time series, capital K is the lag, how many lag you use in your statistics. So the setting we deal with is the simplest one. Say epsilon t are independent normal, yeah? And we, as I said, use empirical distribution with sample size 2000 to approximate the true distribution. Then we report the error, say the mean value of the two distribution, variance of the T distribution, and the quantiles of the two distribution. How we report it? We report the relative errors. This is approximated value, say mean. This is true mean divided by true mean, then times 1. And this is the kind of percentage errors we have. Okay, before I show you the method, I show you the results. The takeaway message is this chi-squared approximation matches the mean value of those true distribution well, but inflates the variance enormously. When variance is larger, what it does is push the distribution apart, further apart from the center position. This makes the critical value too large. That's why those tests become powerless in the high-dimensional case. So what we are saying is the chi-square based tests are too conservative to be useful when p is large. So-called p is larger than p is larger in relation to n. Okay, here is the result. Relative error percentages of approximating those true distribution by chi-square. We only report the result k, capital K equals 3. Yeah? And this is p. This is p over n. Say this is a p equal 10, n equal 100. And then we increase the ratio. In this case, say p is 90 and then n is 100. So p and n are very close. So what you can see, the relative error for mean value actually is not bad. Yeah. Even say p is large in relation to n, approximation for mean is pretty good. But approximation for variance is poor. This is a percentage. Yeah, the relative error is huge. It's over 9,000%. Then you look at the 95% of quanta. Actually, this is what really matters. But when we do the test, we look at this is critical value. And there is inflation by a small percentage. A small percentage in this case matters because the quanta value itself, when p is large, because this is the degree freedom, p squared times k. The quanta itself is large. Small percentage of inflation make the critical much, much larger than original. That's why the test become powerless. I give you an example. In this case, this is the quanta value, 300. For p equals 100, the quanta is 3,000. So small percentage of inflation make a huge difference. Okay, I only report the result of Q2 and Q3 because Q1 performed even worse. Yeah, so that's a problem.
Will it be better if you choose K large in relation to K also need to divert?
In this case, doesn't help. Yeah, we didn't have that. Yeah. Any other questions? Okay, so another concern, because the degree freedom is p squared times k, the p is a dimensional time series. If we have a situation, say like correlation or non-zero correlation is sparse. The trouble with this test statistics, there is one dimension it counts, it inflates the degree freedom. So if the correlation are sparse, non-zero correlation all occur at a few places, but all the zero count in asymptotic distribution, which is another problem. Yeah, even you don't require p is very large. Even in the finite dimensional vector case, the chi-square approximation works poorly if you have a sparse correlation situation. So for sparse situation, intuitively, you can use the auto cross correlation just look at the L1 norm instead of the L2. Just pick up the maximum correlation. So this is kind of problem we have. So what we propose here is just to use the maximum cross or autocorrelations. Just remind ourselves, this is a correlation matrix. And what we do is we define a T and K, which is the maximum correlation at leg K across all components. That's times square root of n. Why we do that? Because we know under H naught, say white noise with some additional condition, this quantity is asymptotically normal. Yeah. So we find the maximum one for fixed leg K, then we run through from leg 1 to leg K. So what you can see is actually for each fixed K, we have p square approximately normal random range. Yeah? So you line them up as a p square line vectors. Then you add one to another from leg 1 to K. So what you end with a capital K times p square long vectors. Each component is approximately normal. We look at the L infinity norm. Okay. So this is our test statistic. Okay. The question is, we need to work out the p-value for this test statistics. So if we know CV alpha, then we have done. How we do that? This is a normal approximation. As I said, intuitively, what we have is a capital K times p square long normal vectors. We take L infinity norm. Therefore, to simulate the p-value, what we do is we try to figure out what this long normal random vector is. Say its distribution is 0 and is pi n. Yeah. Then we can draw from this high-dimensional normal distribution. Then each draw we take the infinity norm. Yeah. So this is like a bootstrap idea. And then you just take the top alpha sample quanta as your critical value from this distribution. So it's very simple. The idea is the key is to prove something like this. This high-dimensional random normal distribution, L infinity norm greater than S, and this is Tn greater than S. Those two are close with each other for all S. So this is what we need to prove. Now have a look how this matrix look like. And this is a canonical product identity matrix times W. W is normalized marginal variance covariance. Yeah. Then inside what you do, you vectorize each autocovariance function. So each of them give you a p squared long vectors. Then stack them up. So this is the capital K times p squared long vectors. This long vector, it's covariance matrix. Okay, it's in the middle. So this is how this is constructed. Okay, we were going to prove that this property holds. Once we have that, we just draw from this normal distribution and do it in the standard bootstrap way. I think it's clear? Yeah, okay.
So here K is fixed or K is
Yeah, we treat K fixed.
Okay.
K goes to infinity, things become much messier.
Okay.
Something? Oh, okay. Let's look at, we have said the technical condition. Let's look at the technical condition quickly. First one, we require all observed the data has a variance. Variance has a uniform rho bound. Yeah. This is because we need this uniform convergence. And basically, this requires all components are not degenerate. And second, we try to bound the tail of distribution. This is weak and sub-Gaussian. Oh, one is 2 is sub-Gaussian. Okay. So basically, we need this exponential type of upper bound for the tail. And the condition 3 is a bit more interesting. Because as I said, for the classical chi-square test, we always require IID condition to prove the validity of the test. But here we don't. We allow this epsilon t. We require the beta mixing, which is a kind of weakly dependent property. Yeah? Weakly dependent. This is not linear dependent. This is kind of including nonlinear dependence as well. So there should be white noise and H naught. They can have nonlinear dependence as long as those dependencies is weak. Mixing condition basically says if you look at time series at 2 points, the distance, the time distance between 2 points goes to infinity, the dependence goes to 0. Okay, so that's mixing condition. So beta mixing condition is not so strong because, for example, Arch-Gauge model fulfill this condition. What we are saying is our test can be applied to test white noise, which are not IID, like say Arch-Gauge model. Yeah, Arch-Gauge are white noise. So this is valid white noise test. Condition 4, yeah, let's skip it. This is just for the technical convenience when we do this uniform convergence. Okay, another pre-step for applying this test. Actually, this, as we will see in the simulation, this makes a difference. The way we use statistical is look at the maximum correlation from lag 1 to lag capital K and across all components. So what we try to do is to apply a time series principal component analysis. The difference between this one to the standard principal component analysis is the following. When we apply standard principal component analysis, it transforms P random vector into P uncorrelated one. Yeah? So you can think this way. What happened is the original kind of correlation, if you see the correlation is the energy between two variables, has been pushed into those components. Yeah? Into those components. When we do it for time series, we require the same idea. We do orthogonal transformation of original p-dimensional time series. After the transformation, you have new p-time series, p-dimensional time series. Ideally, we hope those p new time series are uncorrelated at the same time and close all time lags. So therefore, we do the transformation, we transform a p-dimensional problem into p univariate time series because there are no linear correlations. We can deal with separate. Why this is appealing? Because this kind of transformation push the energy, the correlation across different components, across different laggers into those p individual directions. So if you search the maximum correlations after the transformation, typically maximum correlation increase compared to original. The bigger maximum correlation make our test more powerful. And this is what we call the time series principal component analysis, and there is a package in R. Of course, I should say, this transformation is not always possible. Once you don't have this kind of transformation, what this procedure does is to find you the best approximation in some sense. So what you have is you still have some kind of close correlation among different components, but those correlations are typically small. So this is what. Okay. So this is kind of pre-step, and we find that the time series principal component analysis really serve as like principal components analysis in the multivariate analysis. Before you do the multivariate time series analysis, you apply it, and typically you make your inference more powerful. Okay, now we need to estimate this nasty, humongously large covariance matrix. So this part is easy because this part is the marginal variance. Yeah, you can just use the estimate for each time series variance, then plug in, you get an estimate for this W. This part is easy, but this part is more demanding. So what we have is we vectorize the autocovariance at the different legs and line up. We need to calculate the long-run covariance of this quantity. And luckily, there are lots of study for this covariance matrix estimation. What we use is a standard kernel type of estimate, kernel type of estimate, which using this is a kernel function K, and there is a bandwidth here we need to choose. But this has been, as I said, has been intensively studied in the econometrics literature, and there are Andrew in 91 paper recommended to use this kernel with the bandwidth which is determined by data in a very complicated manner. Yeah, but those are standard procedures. You just take them and apply them. Andrew's proved those combination has some nice properties. We just use this procedure to estimate it. Computational issue. Yeah, let's look at this matrix. It looks very sort of complicated. Yeah, because this is as I said, a capital K times the P matrix. In order to generate a normal distribution with variance of this, you need to store this information in the computer, and it's costly. As I said, the difficulty of computation is this, and the standard procedure to do that is to do a decomposition of this big matrix. Then you work out L, then you generate so many independent random variables, then you apply the transformation to do that. So this requires a lot of computational power and a lot of storages. And there is a small trick you can play, which is say, I'm not going to try to expand everything because actually it's not so bad. So we know the normal distribution has this nice property. Once you have a variance covariance matrix, and if you can sort of decompose it and apply the square root of the covariance matrix as a transformation to standard normal, then you get it. So it's not quite like that, but something similar like this here. Yeah, you take part of the dependent structure, which is dependent on the data here as a condition. Then what you do is you just generate n-dimensional normal random variable. Okay, n theta is the n minus capital K. Yeah, capital K is fixed. So basically, it's an n-dimensional random vector. According to this normal distribution, variance covariance matrix is determined by the kernel function. Okay. The other part of structure is here in F, is here. But this will not change when you have the estimated version. So in this way, you reduce a problem to n cubic hard, which is still computational intensive procedure, but much better than before. Okay, asymptotic properties. So what we have presented here is one is to say, okay, under H naught, this choice of CV alpha using the bootstrap is a consistent one. And the second theorem says it's asymptotically power one if H naught doesn't. There are lots of technical conditions. And some conditions are easy to understand, some are less so, like this, because you require the maximum correlation, which is big enough in order to have enough power. And those are two asymptotic results. Okay, let's look at some simulation results. Method of compare. We have proposed this new test based on a maximum correlation, which is Tn. And we apply what we said, this time series principal component transformation first. Then we have a Tn star. So there are two versions of this new test. Then we also compare, in the paper we compared with Q1, but in the slides I didn't include Q1. Otherwise, the table becomes too big. Yeah. So Q2, which is a Hosking modification of Box-Pearson, and Q3, which is DM-McLeod modification. Then other popular tests in the context of the white noise test is Lagrange multiply test, which you can see in Luc Pong's book of multivariate time series. And George Diao and Box proposed a likelihood ratio test. So when you test the white noise, you can think the H0 is white noise, H1 is AR1 mod, vector version AR1 mod. So this gives you a likelihood, assuming the innovation is normal. Then you can do a likelihood ratio test. So we always set the level at 5% and sample size 300. The p dimension varies from 3 to 150, and lag, that's how many lag we use, and 2, 4, 6, 8, 10. And for each setting, we replicate 500 times. Okay, this is the comparing the empirical size. We set the nominal level at 5%. Then this is the data, which should be white noise. Epsilon t equal a zt. Zt are independent 0, 1. And this is IID. Or independent arch 1. Each component is arch 1. Then this is a white noise, but not the IID cases. And A, we use 3 different settings. This is like, say, decay exponentially when you move away from the main diagonal. This is like a block diagonal structure. And this is just to say, blindly, uniformly -1 to 1. So why we put A in front of that T? This will make the components of epsilon T correlated with each other. Yeah, instead of say everything is IID. Okay, that's the kind of setting we have. And this is the normal innovation. Assume epsilon T is normal. In this case, it's genuine IID white noise. And nominal level is 5%. So this is the model 1. This A matrix sort of exponentially decay when you move away from main diagonal. This is block A. And a block diagonal A, this you can uniformly A. So what you can see is for the Q2, Q3, and Lagrange multiply and the George Diao box likelihood ratio test, when you increase the dimension P, sample size is fixed at 300, then the level is 0. Yeah, it's too conservative. Why we don't have here? Because when you do Lagrange multiply test, you require P cannot be too small. Otherwise, the linear regression, you don't have a unique solution. So that's why you don't have a result here. And for the likelihood ratio test, it's independent to K. That's why for each P and N, you only have 1 value. So for model 1, you don't have. And for model 2 and model 3, it's all the same story when P is large. The approximation for level is poor. Now let's look at the Tn. Tn works better than those conventional tests, but much worse than the Tn star, because we want to see 5. Tn star is say we apply the time series principal component analysis first. We hope the power will increase, and here you also can see the level approximation is much better. And in all 3 settings, it's the same story. This is the arch innovation. It's not IID, white noise. The pattern is similar. Actually, when P is not that large, the chi-square approximation is not too bad. So this, I guess, is the case. The theory is behind the real potential functionality of the method. We cannot prove that those chi-square test is valid for non-IID innovations. But simulation here and also reported elsewhere, that if you have a non-IID white noise, it seems also work fine. But of course, when P is large, dimension is large, then it's too conservative. And again, doing a transformation, you have a better approximation than not. And to compare the power, so what we have now, model 4 is the vector AR1. So in this case, we will expect that the L box test is most powerful because likelihood ratio. Yeah? You can't do better than that. And this 5 is say epsilon t is AZT transformation. And ZT actually for each component of ZT, and ZK1, ZK2 to ZKN, there is dependent structure there. So each component is a time series, there is a serial dependent structure there. And we define A in different type, but that's not important. So what we can see, this is solid line with square is the new test we proposed. Solid line with the circle is say we apply time series principal component analysis first, then apply the test. This is the test for, this is the likelihood ratio test. In this case, is optimal. X-axis is capital K, different laggers. For likelihood ratio test, it's a constant. Or the same. And those other 3 are Q1, Q2, Q3. Yeah, Q1, Q2, Q3. And as you can see, when the P is large, they don't have power. This is because of the significant level. The critical value has been inflated. So those are nothing wrong, nothing that much wrong with the statistics as for the setting we specified. But this is simply because of the poor level approximation. And this is model 5. Okay, that's model 4. But when P is large, the pattern is always the case. The classical testing you cannot use. Okay. Application to the model diagnostics. So what we have done here is we present a general theory. So there's a regression model, YT, and XT are observed regressors. The G function itself, we know completely. What we don't know is theta. We use the data to estimate the theta. In the context of time series, UT is the laggard value of YT. Then, as long as the estimate for theta naught fulfills some condition like this, then when you do estimate, calculate the residual, apply what we have said so far to the residual. All results we talked so far still hold. So this is just to say the procedure proposed can apply to modern diagnostic checking, but all those are sort of technical conditions. Okay, I think I'd like to say I still have plenty of time. Yeah, that's good. I'd like to say a few words about the second paper, which
Can I ask a question
sure.
first? So I was wondering, when you do your TS-PCA transformation, you could also just keep the largest principal components, right? And then, like, does that, first of all, does the theory work? And secondly, does that help computationally? Because then you're only generating normal random vectors from a lower dimensional space.
You said you applied TS-PCA?
Yeah, instead of mapping it from P dimension into P dimension, maybe you map it from P dimension into lower dimension.
Yes, I didn't think this way. Then okay, put it this way. We didn't prove, say, the procedure. When you apply the transformation, you are not working with original data. Our theory, what we have proved is with original data. When you apply TS-PCA, only choosing those, you're quite right, information are in a few components rather than say, the rest is just like white noise already. And I guess, strictly speaking, in theory, you need to prove that the procedure still works because already there is a kind of extreme value idea carried out there. But I think in practice, it will work well. You don't need to worry about look at the last few components, which actually are redundant. You never see the maximum correlation goes to the last few components. You're right. But I don't have a theoretical justification for that. Any other questions? Okay. So this is using L infinity norm. And when I talk to those guys, in the first place, I said, what I really like to do is to come up with a function, matrix function, which summarize all correlations, cross correlations over different leg together. Then we work on this function, work out the maximum eigenvalue. If this maximum eigenvalue is 0, then it's white noise, very clear. It's just a univariate quantity. But we never be able to crack that problem. The problem proved to be theoretically too hard. So this is the attempt we come up. It's not ideal because we compromise a lot in a way. But what's remarkable about this random matrix theory is the approximation provided for the level is much, much more accurate than the normal approximation. So let's see what we have come up. We know the random matrix theory is nice and beautiful, but typically we have the nice results with a simple setting. Here, this sort of spirit shows up again. We need more conditions. We cannot do like what we did before. We just talk about white noise without assuming any kind of structure. Here we need a clear structure. The time series we are concerned is a linear process. Sorry. Where we are. Okay. Is a linear process. Xt is a constant matrix A times Zt. And those Zt are independent. Okay? We don't require identical distribution, but almost like an identical distribution. First moment is 0, second moment is 1, and fourth moment is constant across all components. And the variance covariance of Zt is sigma naught. We test white noise basically says Xt is Zt. Why I write this way? This must be an error. It should be A naught. It should be A naught. Here is A naught. A naught Zt. Then Xt is the IID white noise. Yeah, so it should be A naught. Then you calculate the sample covariance matrix because we assume mean value is 0. Yeah, the sample covariance matrix like this. The test statistics is in this form. Instead of using the, I write abusable notation here. This sample covariance matrix I write as rho ij hat. Okay, so instead of using the sample correlation, I use the sample covariance. Because if you normalize it, the random matrix theory cannot cope, which is a pity. Okay. And but this problem is a trace of this matrix. You can put the trace outside. Yeah, you put trace outside. What you have is that this actually is the eigenvalue, is the sum of eigenvalue of a positive definite matrix. So this is where this random matrix theory can kick in. We recast the problem as a sum of eigenvalues. As I said, what we really need is just the maximum eigenvalue. It should be sufficient, but here we have to do a sum. And second, as I said, it's not correlation based, it's covariance based, which is not high. But test statistic is more or less the same as the box portmanteau test. We have seen this Q1, Q2, Q3. Okay, the paper has a result for general case, really dealing with the sample covariance functions. But the results become a bit more involved. For the simplicity, I only give a simple case. So assume, say, the variance of xt is an identity matrix. So before you do anything, you standardize your time series. Yeah, make it sort of variance. All components is 1. They are uncorrelated at the fixed 0 lag. Yeah, this can be done. So in this case, the sample covariance matrix is the sample correlation matrix. It's the same. Okay. The statistics, as I show you, is just this. In this case now, is sample correlation squared add up, like box portmanteau test. Then this test statistics minus this bias term and asymptotically normal with the variance in this expression. So when you look closely to this formula, all quantities are given, except you need to estimate the force moment of xt and the h naught. And this Cp is just a proportion of p over n. Yeah? So everything is given. Under h naught in this simple setting, the problem is easy because under h naught, xt equals zt. To estimate the force moment of zt become trivial. You just add all those sample force moment together. But when sigma naught is not IP, things are more involved. This mean value and this mean value and this variance involve those quantities. This is much harder to estimate them, but there is a way out using some random matrix theory to get consistent estimate for these quantities. So this is what we presented in the paper. Okay, I just show you one result. This is the empirical size at 5% level. And you can see for k equal 1, k equal 3, when p is large, it's very close to 0.5. And all classical tests we know don't have a power. So this approximation is much more accurate. Surprisingly, to us, it's so accurate. And the drawback is it's require much stronger condition. We only can test the IID white noise, not say the genuine white noise. And the two tests actually are try to catch different characteristics of the time series. The first one is for sparse case. If the correlation is sparse, you use first one. The second one is sort of correlation are more sort of spread out everywhere. You add them up. Yeah, I'll stop here. Thank you very much.
Questions for Qiwei?
The theory of the first part can also handle the situation when p is larger than n.
In theory, yes.
But in numeric,
Works very bad. We can handle p is at an exponential rate of n, yes.
So I think it's because the extreme type of the test statistic has set distribution, right? And is there any way to solve this? Even with like the TSPCA still under low dimension.
Sure. Actually, Ray K, after we had these two papers, he sent me a paper using extreme value theory to do these things, high-dimensional white noise test. And he said that when he saw what I did, he had a similar sort of inkling like you. So he started this extreme value theory. I had a look. I didn't quite understand the theory, but I don't know. But he also reports some numerical result. Works pretty well. Yeah. Certainly there is a mileage there. I think his paper is online. You can search it. Yeah.
Okay, well, let's thank Qiwei again.